Should I start? Okay, yeah, thanks very much for staying until this point. And I believe this is the first time we're going to talk about the technical details of the platform we're building. So consider yourself lucky. And I hope I'll say something interesting. Okay, so this is a platform we built at Uber with the whole machine learning platform team, which is headed by Danny here. So I'd like to acknowledge everyone in the platform team. I mainly want to talk about how do we scale the machine learning as a service at Uber. I'll tell you why we do that and how we do that, some of the technical details. So our goal, I guess you have heard for the things yesterday, and if you want to do machine learning and you don't want to do the old way, which you have a lot of difficulties in scaling it up, right? So you want to democratize machine learning where everybody, including engineers, data scientists, or even analysts across the whole company to be able to build and deploy a machine learning solution and very fast, right? So that's our goal. And so I'm going to first give an overview, and I'll use a particular example we have, which is the Uber Eats app to estimate the time of delivery, and so to illustrate the whole system. And I'd like to get a show of hands. Who have used Uber Eats here? Oh, OK. A few. Who have used the Uber app? OK, great. Yeah, and then I'll talk about the machine learning workflow and our architecture. I'll focus on the specific challenges we have, and I'll conclude. So we want to build a machine learning as a service instead of a library, right? So I think people typically don't make the distinction between library and service. Service is actually very important for us because it's very interactive. Analysts, data scientists, engineers can actually come to our platform and just basically using the UI, they can create their models and iterate on it and deploy it into a real service, right? So because we kind of operate globally, we have a pretty large scale, and we're growing very fast. So we have to design our system in a scalable way. And a lot of our kind of models can be trained on a single machine, but there are also models that we need distributed training, right? So we want to design a system that handle all these different use cases. And so as all the people you already kind of know that you do need workflow tools to actually make things easy, right? Because simply, like keeping track of the model manually is kind of a pain, right? So I have to automate the whole workflow. And so our platform is built in the context of traditional machine learning and deep learning. And I'm going to focus on traditional machine learning for this talk. And it can also handle online reinforcement learning, but I'm not going to talk about that in this talk. And so since many of you haven't used this app, so I'm going to just show you how it looks like. And so this is the API when you log into the app. And there is a small feature here. It says, once you if you place your order, it will take this much time to arrive. And so once you make the order, right, so that you get this API, which says, oh, I'm confirming the order with the restaurant. Then at this point, you can cancel. And then there's food is being prepared. And then, finally, food, arrives your time to eat, right? So, and from confirming order to its arriving, that's the time. And so this is sounds like a simple feature, but it's actually a lot of technology behind it. I'm going to show you how we did it. So I guess I don't want to repeat a lot of these steps. You have probably heard enough. And so to build a machine learning solution, you have to get your data, and then train your model, and then evaluate, deploy it, and then monitor it, right? So the whole process. And there's, in terms of high level, there's nothing special what we do versus what other people have been doing for machine learning platform. And I'm going to focus on the more technical details and how we did this, right? So this is the system architecture we have, and so this is the batch world, right, where we we get data from our data lake, right, say Hadoop, and then we do batch training and batch prediction. So, and this is kind of standard technology. We have Hadoop, and so in order to get your data, you can write a Spark job, right, do the ETL to prepare your data, and you can also write a SQL query, right, say against Hive to get your data. And you have to get two pieces of data, right? You have to get your features, right? And then you also need to get your ground truth, which is the label. So you could have a single Spark job that generates the two data sets, or you could have two SQL queries and generating the two data sets. And these two data sets are used for batch training, right? So for example, you can use Spark, the MLlib library, to train your model. And then once you train your model, you can actually do batch prediction, right? And you can sort of write your prediction result to Hive or Kafka, right? And so this is the batch training and batch prediction world. And to really simplify how we get our features, right? As most of you who do machine learning, you know that getting the data is actually getting the feature into a form that you can use for training is a pain, right? So, rather than having everybody to go through the process, because we have our specific sort of application. So if some other people think this is a useful feature, and then maybe some other team will find it useful as well. So essentially, we can actually share these features, right? So we have an ETL process. We can compute these features a priori and put it in a feature store. Right? So this is kind of a offline batch computed features. And so the good thing about this is that like when you build your machine learning models, you can actually reference these features, and you can quickly iterate, right? Because it's available, right? Otherwise, if you want to add a new feature, and if you have to change your data prep job, right? So if you're kind of need 2 months of data to train a model, then you have to backfill it. That takes a lot of time, right? So, and so we also have the real-time world. So this is like batch computed features, kind of offline, right? And then there are also like real-time features, right? For example, in the Uber Eats app, so we want to know how many orders has been processed for the last 5 minutes, right? So for that, we cannot do it this way. So we have to have a streaming engine, get our data in a streaming fashion, and write it to a sort of database that handles point queries, right? And so this, real-time features, you can actually reference it in the batch job. You can also reference it in the prediction. So our client service, the Uber Eats app, the backend is gonna really talk to our prediction service, and the prediction service is gonna use the real-time feature, right, to do the prediction, right? So instead of each application computing these features by itself, once we pre-compute it, all the application can use it. And so this is the whole process of getting data, train model, evaluate, and deploy, right? So in terms of how do we control this, how do we monitor, we have a monitoring console where you can actually come to the web UI to create your projects, right? Create your data, and then so do the whole thing. Very easy. And so we also have a Python client, right? It's like the Databricks notebook, which can talk to, our platform, right? And which, instead of the IPython notebook, which you cannot do parallel processing, right? You cannot parallel train your model. You cannot really parallelize your data prep. So here, we kind of augment the IPython notebook so that you can actually, in parallel, train your model and do your data prep and iterate, right? So because our web UI may not be the best, way to do the iterative process, and this provide a easy way to iterate developing your model. And so once we put the model in production, we actually have to monitor it carefully, right? So we have our own metric system, essentially is a time series database. And so that time series database powers two things. One is alerting system, right? So the alerting system will read from the time series database. It will look at the metrics, and it will alert on-call engineers. And so here there is a dashboard. You can actually go to the dashboard and look at how well your model is performing, right? So that's the whole system. So I'm going to sort of progressively getting into more details of our application, example application, see how it actually leverage the whole platform, as you can generalize to other machine learning use cases we have, right? So here, for the Uber Eats estimate time delivery, and so the pipeline is like this, right? It's we have too many boxes before, and so now you can sort of visualize in a high level. And so in terms of training, and the model gets features from the batch feature store, which is Hive, and also gets from the real-time feature store, which is Cassandra. And they also have the, you can also have data prep jobs. Let's say it's a Spark job that produce the features. So all these features gets used by model training, and then you can deploy the model, right, in the real-time prediction. The Uber Eats app is gonna talk to the model, right? The model is deployed in the Docker as a service. So I'm gonna get into that in more details, and then you get your prediction. So a little more details on how we do feature engineering. And so you probably have heard the domain-specific languages where you can transform raw features into the actual feature you can use, right? So you have to handle missing data. You have to handle, let's say you have time that's in the different formats, right? You can actually transform these into a standard format, and then prepare it for the model, right? Because if you know some of these tools like MLlib, right? So they they need the data in a certain form, right? So you have to handle, say, some of these categorical variables and all of these things, right? So that's the function of domain-specific language. And having that is not enough for us. And as I mentioned, we want to make it easy to engineer features, which the key thing we have is a feature store, right? So the feature store serves many purposes, like I said. And so typically, so data scientists, they're trying to engineer the feature, right? So because, we have the same data set, we have, similar applications, right? So we want to, the feature store enables people to share the features and to make it easy to iterate, the model building, right? Because you don't know which feature are actually useful. You can actually quickly iterate. And the third thing is that, when you do real-time prediction, some of these features you cannot really compute in a timely fashion online, right? For example, the average demand of a restaurant, right? The average demand restaurant for the past 2 months, that would be like, take a long time to compute, right? So, that's, I just want to stress that the feature store is actually very useful for all reasons I mentioned. And I'd like to illustrate more about the details of our pipeline and how the DSL fits into the picture, right? So here you got your Spark job that take the data from the data lake. You get your basis feature, right, which we call basis feature, kind of raw feature, and then you use the DSL to get the transform feature, and then you feed it into the model, right? And then you make predictions, and the feature store fits here, where the DSL can actually reference features in the feature store, right? The DSL, works the same. It doesn't matter whether it's raw feature or feature store feature. It's just like it has a different name. So it simplifies, the sort of feature engineering for people. I wouldn't say data scientists because now everybody can do it. So to get into some more details, and as you can imagine, to actually make predictions on the time of delivery, right? So there are a lot of features you have to take into account, right? So what are the features? There are some restaurant-specific feature, like where is the restaurant, right? And the average meal preparation time, right? The average delivery time, and the average demand during lunch. So as you can imagine, some of these are kind of aggregate features that, if average demand is for the past 2 months, right? And so, we don't want to compute it on the fly, right? So, these are kind of the batch computed features in the Hive feature store, right? And they're also like contextual features. As you can imagine, the time of day is very important, right? So during dinner time, there'll be like a surge of orders, right? So, and then you have also the order features, like, which dish you ordered, right? Some takes time to cook, right, as you know. And then the near real-time features, let's say for the pass-in orders, right, what people ordered and how long did they take, right? If you have some popular dishes, it's probably going to slow the ETD down, right? So, you have to take care of all these features. And as you can see that this is from the real-time feature store, and there are some of these contextual features that's really supplied by the app, right? And the order feature also supplied by the app, right? So that's some of the real-time data we have. So, and one of the things people often look is that how are we going to train models and manage models, right? And so for us, we operate in more than 400 cities, right? Let's say, if we actually train a model for each city, right, and then manage 400 models, right? So that would be like really time consuming. Well, in terms of accuracy, that's actually not the best thing to do as well, right? Because we have data from many cities, right? Why can't we actually leverage all the data to increase the accuracy of the model performance, right? So for many of these reasons, we actually develop partition models, right? So what it means is that you can actually build a hierarchical structure and, for example, partitioned on the location, right? So there'll be like the leaf level will be like, say, cities, right? And then you have country, then you have the global, right? So you don't have to partition this way, but it's one way to partition your models, right? So each node you can think of as a model. And so we have, let's say we have Boston, we have San Francisco, New York, right? So, and at the leaf level, so what we're going to do is we're going to train all of these models, right? And so why do we train all of these models is because that, there are a lot of reasons. Sometimes the global model is better than the local model, right? So anybody take a guess why sometimes the local model is not as good as global model? Exactly, that's one of the reasons, right? And yeah. So especially, we're kind of a young company, and so a lot of the cities we just entered, right, we don't have enough data. And so essentially we're going to fall back to the more regional model, right? So how we do this, we split the training and test data at each node. And we're going to build a model, right? And then we evaluate the performance. And if this performance is not good, we're going to fall back to the parent, right? If the parent is not as good, and then we fall back to its parent, right? So, and at prediction time, we're going to use the best model, right? We can deploy all of these models, but we're going to, depending on which city, and we're going to use the best model, right? So, yeah, that's a sort of model building. And because our service is sort of real time, right? You open the Uber Eats app, we have to predict how much time for each restaurant to get you the meal. And so we have to basically deploy the model in a real-time service. But what we do here is actually, on the high level, pretty standard, right? We kind of deploy these Docker containers using Mesos. And so we deploy 1 or 2 models. And so there's load balancers. The Uber Eats app, the backend, is going to talk to these containers using the load balancer. And so as you can see that this prediction has the domain-specific language and and also talks to the feature store, right? So this is the same process as we do for training, right? This is actually very important. And so to actually get the same result, right? So oftentimes people create APIs which are different, right? Let's say you're sort of when you're training, you have a different API. When you're prediction, you get a different API. So that often confuses people that you will not get consistent results, right? So we purposely create the same API for both training and prediction. And we have sort of some detailed, interesting techniques where if we deploy a new model, you're gonna just hot swap to the new model. And we also have optimization techniques that essentially deploy the model very fast. So I'm not going to go into that. I can talk to you offline. So this is a performance number. As I said, we train a partition gradient boosted tree regression model to predict the estimate time to delivery in the Eats app. And so if we measure the latency from the client backend, our 50th percentile latency is just 7 milliseconds, right? So 95 percentile is 15 milliseconds. I think we got a pretty good number. We can further optimize, but at this point, we're pretty happy with the numbers. And to conclude, we build a scalable machine learning as a service system. We actually make use of a lot of these open source components as we see fit. And we sort of build on top of them and to handle our specific use cases, and especially the scalability challenge we face. Scalability not just in terms of model training, but also in terms of the time that people like engineer data scientists spend on working on it. And there's also other scalability like the latency, right? The latency of prediction and the latency of deploying the model. And all of these we count as part of the scalability challenge. And so all of these are very important, right? So people typically think scalable training is the most important thing, which, like other aspects also pretty important, right? So we made it very easy to engineer features and iterate on the models and manage the model, right? Especially the partition model, right? Manage it as a whole so that it's much easier to actually, reason and deploy. And also scalable real-time prediction service is very important if you have real-time services, right? So, we use some of these, generic techniques like load balancing across containers without global state. But we have certain optimizations to allow fast, really one-button deployment, right? It's actually a very fast deployment process. So especially when we iterate on the model, it's going to be very important. Yeah. Yeah, that's the end of my talk. Yeah.